Hey guys, can you hear me?
Yes.
Okay, great. Thank you. Okay, let's see.
Hey, Professor.
Yeah, hi.
I had a quick question. It's kind of related, kind of not related, kind of just
Okay.
for fun.
Uh-huh.
So I know that there's like a global semiconductor shortage right now, and like that's why it's so hard for me to like get a GPU or like my PS5. And I
Uh-huh.
know it's like because of like the increase in like consumer electronics because of the pandemic, but like that can't be like the only reason, right? And I thought like you'd be a great person to ask if like other reasons for why the shortage is so bad right now.
That's the story. I don't know if I have a better story for you. There's also a trade war going on with China, and a big part of it is over semiconductors. Um, so you don't know, I don't know like how much of that is affecting what's going on. But anyway, the official story is, yeah, like you said, that because of the COVID, there's people working from home, and so there's been a like huge amount of investment from companies. So every like people working from home, they need PCs and laptops, and the companies need more servers and firewalls. Just sort of like ripples through the system, and so that's the official story. And then China, like I mentioned, there's like this war with China, trade war, not a hot war yet. So I'm sure that's affecting things. It's like a interesting thing that happened to me a long time ago. Maybe it's kind of a funny story, but I remember because it's you have this. There's essentially uh, let me get into the deep version of this. So there are only really okay. Let me take another step back. So there's two business models for making semiconductors. One of them is companies having their own factories. That's a company like Intel. They have their own factories. They live or die with like how well those factories do. Most people use factories outside themselves, like companies whose only job is factories, or that part of their business model is factories. So, and there's only for things like GPUs and these high-end stuff, there's only two of those companies left in the world. Only two, which is frightening. One of them is in Taiwan. It's called TSMC, Taiwan Semiconductor something corporation, and I think they're the provider to NVIDIA. Okay, so that's just one. And then Samsung makes their own chips, but they're also a big provider of chips for outside people. So basically, have only those two. And those two guys, what happens is when you get like a hot product coming through, they might bump other products while they're fulfilling those orders because they don't build their capacity. It's so expensive to make these factories. They don't build their capacity to support peak demand. They build their capacity to support sort of average demand. So when the fabs get full, it just seems like that it just things get like the delays are a lot longer than you think. So I don't know if I hope that helps, but like I've seen like there was one other time this happened was like 98, 99, where you like, man, it was like if you wanted to buy an op amp, it would take like 6 months for delivery, and that was just crazy. So,
Oh,
so
wow.
you're
Yeah.
waiting on your stuff.
I'm sorry. What was that?
You're waiting on your stuff now.
Yeah, it's so hard to get GPU. It's so hard. But yeah, it's just really interesting.
Is it like an NVIDIA thing?
It's a both thing, both GPU scenario thing.
Yeah, AMD, NVIDIA. It's just super hard to get like the new cards.
Interesting. Yeah, I don't know if I mentioned that to you guys, but so sorry, I can't multitask. Let me try this before I get started. So there was a story in January. I think it was a Volkswagen line? I think it was a Volkswagen production line had to shut down because they couldn't get chips for their car. Okay. And like that doesn't, it just seems like, well, you kind of shut down for a while, we get the chips. But I'll tell you another story. So we were doing business with a company that sold parts into automotive companies. And their CEO, as we were signing our agreement with them, the CEO was telling me the importance of us always being on time and not disappoint the car companies. Because the car companies, they got to have their stuff because it's very expensive for them to shut down their production lines. So he was using an example of, I forgot if it was Ford or somebody like that. They had to shut down, and I guess everybody in the automotive business knew this somehow, that they had to shut down or production because one of their vendors was slow to produce. So what Ford did was they would fly a helicopter back and forth, just picking up like whatever parts they had and flying it back and forth just to keep, whatever they could get. And at the end of that whole process, they sent the bill for this activity to the vendor.
Oh my goodness.
Isn't that very inefficient?
Yeah, I mean, but the thing is, like, for the automotive companies to shut down their, like, imagine like this is stuff they're selling for, I don't know, depends on what a VW costs. Let's say 30 to, I don't know, like say $30,000 to $50,000, depending on the VW. Maybe it's $20,000 to $50,000. Each car is just sitting there when it's not shipping. I don't know how many parts they ship, how many cars they ship per day. But if you have like a part that costs $1, can stop that. And imagine if like you can't ship anything for like a week or 2 weeks. It's like a very, very, very expensive problem for the automotive company. So anyway, it's just like really bad things are happening all over. There's I don't know if you guys know the Economist magazine. I get it. It's a great magazine. They actually had an interesting article. I'll see if I'll try to post it for you guys about the economics of the semiconductor business and how just these two facts that there's only two factories that can make these anymore, like especially the high-end parts, and this trade war with China is like potentially like can cause all sorts of really bad supply issues. It's interesting in a bad way, but anyway, that's how it goes. The semiconductor market's kind of an interesting thing, especially the commodity part of it. Okay, so guys, let's get started on. I'm gonna be. I don't think I've posted the new homework yet, but I'll do that hopefully tomorrow, so you guys can get a start on it. So today, I think what we talked about last time was the concept that we had two models for our diode. One of them is, you can think of it as as real as it's going to get in our world, is this, what we call a exponential model. So we have exponential model. And it looks like this. If you put a voltage across our diode, And if you plot the current versus voltage, we end up with something like this. And this is, so let me give you the full equation as, so I sub D is I sub S exponential of VD over VT minus 1. Okay, and I sub S, we had an equation for, it's a bunch of device parameters like doping concentration, so on and so forth. But, depending on whether you're being asked to calculate it, usually like in chapter 3, I can't promise, but I don't think like you'll be given it in chapter 3. From now on, it's, like in the real world, if you're getting, buying a diode, using it, they just give you the I sub S with, some variation. So this is like, again, a very small number. So maybe 10 to the minus 10 to 10 to the minus 17 amps. So this thing is like minus I sub S over here. And over here, very quickly, you end up being this exponent ends up being much larger than 1. So out here, for most of this, I sub out here. So like sort of out here, out here, let me just put it green. Out here, I sub D is equal to minus I sub S. Out here, I sub D is I sub S, let's say approximately I sub S exponential of VD over VT. So you can get rid of the minus 1, which helps with the calculations and so on. Just again, because this parameter ends up being much, much bigger than 1. And sort of around here, or to calculate what this VD on is, or VD on is kind of like the potential barrier. You have to use the full exponential model to calculate it. Okay. So, any questions about this model? Like, you should like remember these equations. I hate to remember anything, but I actually remember these, like just the ID I sub S exponential VD over VT minus 1. I actually remember that. So,
Professor?
so you have to remember it. Yeah.
Where does the minus 1 come from in this equation?
You mean out here, or just the fact that you got this minus 1?
Yeah, like where's that minus 1 from on the equation? Is it just to make the graph go under 0?
Good question.
I mean, I guess a more specific question would be how come it goes under 0 and not just stops at 0?
Okay, but that I can answer. I can't remember what the minus 1 is, but so that I think I might be able to answer. And sort of like in a well, can't get too deep into it, but let's say we had our PN junction. So P and N. So, this was doped with acceptors. This is doped with donors. And so there's a bunch of positive ions left over here. Positive ions. There's a bunch of negative ions left over here. And so you end up with an electric field pointed that way and a voltage pointed that way. Okay, so we said let's say I put a voltage source, but let me just keep it at 0. So but I'll just add it on. And so we can play with it. So yeah, I'll call it V sub D. You with me so far? You agree with everything?
Yeah.
Okay, great. So now also remember that what happens was this built-in potential, basically there's this built-in potential and caused by this electric field is exactly enough so that there's no diffusion current flow. And the diffusion current flow was coming from holes going from here to here. So these are holes. And electrons going from here to here. So they were going from regions of high electron concentration to a region of low electron concentration, and a region of high hole concentration, a region of low hole concentrations. So this electric field, this voltage was exactly enough to stop that current flow. Okay, that's what we said. Okay, now the thing, you know, we kind of, it does exactly eliminate that current flow, but there is another current flow. And that current flow is, although there are majority concentration here of carriers of electrons, although there's a majority of electrons here, there are also holes here. If you guys remember, we calculated the minority carriers, right? So there are holes here as well. Okay, so normally the holes wouldn't like go from here to here through diffusion, right? Because there's more holes here. So we had a small amount of holes here. They wouldn't, by diffusion, they wouldn't want to go there, right? Are you with me so far?
Yeah.
Okay, but now there's an electric field. So if there is a hole that is somewhere close to this junction, and it gets gets pulled into this electric field, it's going to get shot across by the electric field, not by the diffusion. So although it's a minority carrier here, there's very few holes here, there's more holes here. If there's a hole ends up somewhere very close to this junction, it can get pulled in by the electric field and go to this side. Same with an electron on this side. Although this is very few electrons here and a lot of electrons here, diffusion won't carry the electrons over. But this electric field, because the electrons are negative, if an electron shows up anywhere close to this junction, it's going to get shot across by the electric field, so by the drift current. So all this current is actually drift current caused by the junction of minority carriers on both sides. That's why it's such a small current. Okay, it's a very small current because it's just very few of these minority carriers are in this period, and fewer still are going to be close to this junction, close enough to get pulled in by the electric field and shot to the other side. And same with this. Okay, so that's why even at even with the potential barrier there being there, you get like a tiny current of minority carriers going across. Now, what happens as you add more and more voltage here? So if I start increasing this voltage, so initially it was 0, the junction was a certain width. Okay. And we didn't talk about this very much, but we did say it, and it's a fact that as you increase this reverse bias voltage, so as you increase the voltage on N compared to P, this junction grows, but it grows very slowly. So it's kind of like a square root type format. So as this voltage goes higher, this boundary of this junction grows. Means that you'll capture even more of these minority carriers. So if so kind of long story short, if I was just gonna plot, or somebody was gonna plot the diode, so I'm gonna just zoom in on over here. Let's say I'm just gonna really expand. So this is, I don't know, 1 times 10 to the minus 10 amps or something. So very little current, okay, just mind you. So I'm like really zooming in here. So if I was gonna, and let's say this is like minus 10 volts. So a lot of voltage. That's relatively a lot of voltage. You know, the scale is pretty narrow voltage wise, but very wide current wise. So what you'll kind of see is it'll go in and there'll be kind of a slope to this thing. So it'll be a very small value. You know, like it's close to minus I sub s, but it actually like grows more as this voltage goes up. But it's small and it's like a second order effect. So even this exponential model, it just calls it minus I sub s and assumes you stay at minus I sub s. So that was a very long-winded answer to your question. It's just minority carrier drift current. Did that work?
Yeah, that works.
Okay.
Thank you, Professor.
Okay, so this is our, you know, so I think it was nice that Nelson asked that question because it shows you that this is why I call this, as far as we're concerned, this is a real model. But in reality, there's like second, third order effects, and you know, there's like factors here, which, you know, there's a, like if you, I don't know if this is in the book, but some other books, you'll notice like this is just for FYI. It's not in this class. I'm not going to talk about it, but you'll see like an N here, and that N is somewhere between, you know, whatever 0.9 and 1.1 or whatever it is, because, you know, this is also assuming the, you know, the junction is abrupt, meaning that it's, you know, happens very quickly. And then, you know, there's this effect of, there's like a lot of second, third order effects. You know, if you're a semiconductor physics person, you'll be digging into those effects and looking at them. But this is as deep as we'll go in this class, this model. As far as we're concerned in this class, this is reality. So this is our like baseline model that has all the facts that we know. We'll add one more fact, which is, but we'll get to it. But this is, as far as we're concerned, this describes fully the model. We're just going to pretend that's the case. And it, you know, for us, it's the case. Another place you could look at, I'm assuming you guys, I don't know if you guys have experience running SPICE, the simulation program. I haven't decided yet if I'm going to ask you guys to do it here. You'll definitely have to do it in 2200L and stuff like that. But yeah, like LT SPICE, they're all these different P SPICE, LT SPICE, all these flavors are just flavors of the SPICE program, which is like this differential equation solver for circuits. But so you'll have like a library of models, and there'll be like a diode model, and you'll see that it's like a pretty stacked pretty deep with parameters, because, you know, if you're going into a CAD simulation, things get more complicated. You can make things more complicated. But anyway, long story short, I'm just gonna like, this is it. This is where we're gonna stop for, is as complicated a diode equation as we'll have for hand calculation. Okay, and even, okay, so the next thing we said was that even this is too painful for even, you know, very simple circuits. By the way, the couple of things, and let me tell you guys a couple more things to remember. So, you know, remember, you want to remember this. And, you know, the tests are all open book, you know, open internet, everything, but it'll just take you guys too long to go and find these things, you know, in the limited time of a test or a quiz. So it just helps you guys to remember that equation, remember this equation, and then I just, you know, can't be bothered to solve this every time. I remember the reformulation of this equation, which is V sub D is VT natural log of ID over IS. It's the same equation, it's just sort of flipped around, because sometimes you want to find out VD as a function of ID and sometimes the other way around. So, and then lastly, remember that VT is KT over Q. And again, I can't promise 100%, but for the purposes of chapter 3, we're pretty much, and I'm gonna tell you guys, but always be on the lookout for this room temperature. Sorry, temperature is it's room temperature, or you might see temperature is equal to 300 degrees Kelvin, and at that point is 25 millivolts approximately. So these are all the things you want to. I suggest you guys remember. Anything else? No. Okay. And of course, this curve is, remember that. So, so we said, okay, even this model is too complicated. As soon as you start trying to solve some equation or something with this, it gets too gnarly. So we're gonna do a really a simplification, and so we're just gonna. So if I was gonna superimpose, redraw this thing, be like that. And I'm just gonna do like a childish thing and just say, hey, this is called the ideal diode model. Which we'll sometimes use. So basically all this says is if, so let's call this plus minus, so it's VD. So if VD is larger than 0, then the diode is on. Okay, so the diode, sorry, let me redraw this. So you can just pretend like your diode is the same as a closed switch. Did I do this right? Yeah, and I think this is called the, oh, I never get this straight, cathode, anode. If this was a PN junction, this would be the N, this would be the P. Okay, but anyway, if this VD is larger than 0, so we're talking about here, if it's anywhere larger, sorry, it's larger or equal to 0, anywhere here, then the diode is like a closed switch. So what does that look like? It means as soon as this switch closes, that means the resistance of the switch is equal to 0. And you basically, no matter what your voltage is, you'll get, sort of infinite current here, because that's the relationship between voltage and 0. So V is equal to IR, I is equal to V over R, and I is equal to V over 0 or infinite. So it's a closed switch. It's a switch that has 0 resistance. Okay, and then we said if VD is less than 0, then the diode looks like an open switch, or R is equal to infinity. And that looks like so because again, I is equal to V over infinity equals to 0, it's gonna look like a flat line. So you'll get like that. Okay, so closed switch, open switch. Okay, so that's the ideal diode model. And we started playing around with that, and then we're gonna continue to do so like ad nauseum today. Better like have a Diet Coke or something, refresh yourselves, because we're just gonna keep doing example after example of what this thing, like how to analyze circuits with this. I think we did one last time. So the first thing, let's see which one is the first one. Let's do this one. Okay, R1, D1, B out. Okay, whoops. So I always like to put this in the middle. Did I be out? And then okay. Let me find my notes here so I can. Okay, so Here's the approach. It's always the same freaking thing. Okay, so but just practice, 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 and don't take. My advice is do not take any shortcuts, or again, unless you're a circuit genius, you're going to be sorry. Sooner or later, on some quiz or test, taking a shortcut's a bad idea. Don't do it. I don't do it. I try not to do it. So the first thing you want to do is to say, okay, what happens if Vn is very negative? So Vn goes to minus infinity, very, very, very negative. So you don't have to, again, sometimes you have, as you'll see in some of our tests, there's some funky resistor ratios and stuff like that. At this point, you don't want to be thinking about like, what if it's -1 or -2? You want to think negative as heck. So you want to know what state this diode is in. Okay, so if Vn is very negative, if this point is very low, okay, it's going to be lower than that point. It means this diode, that Vd across this thing, if this thing is very low, okay, Vd is going to be negative. If Vn is very low, Vn is going to be negative, meaning that the diode is an open circuit. So I always draw the circuit again. With the diode in the state it's supposed to be. Okay, diode is off. Okay, so what does this look like? Well, you have this R1 between V out and Vn, but there's no other resistance or something like that to drop that voltage. So it ends up being that V out is equal to Vn, because there's no current flow across R1. There's nowhere there would be like, if you look at a KVL, this be V out would be Vn minus the voltage over R1, but there's no place for a current across R1 to go. So there's no current across R1, so just Vn minus 0 is V out. Okay, so that's very negative Vn. Now let's see what happens if Vn ends up being very positive. Okay, so if this guy ends up being very positive, then the diode turns on. Okay, so I'm going to redraw the circuit. Okay. So in this case, V out is just going to be 0, because we're shorting across V out. You guys, everybody with me so far?
Yeah.
Okay. All right. So okay. So those are those two extreme cases. Now the other thing we need to find out, again, don't take a shortcut for this. Like, it seems like you could the first few problems you do, but quickly you'll like regret it when you can't do it. You look at the case where, like, where's the break point? Where do we go between these equations? Is it at 0? Is it at some other voltage? How do we know that? So so what do they call it? The crossover point. Why did I say break point? I call it the crossover point. So when in one case we have this V out over V out is equal to Vn, what does that look like? That kind of looks like a curve that does this. Okay. What does this look like? Well, it looks like this. No matter what Vn does, V out is equal to 0. But where's the crossover? We know when it's very negative, then Vn is very negative, it looks like this. When Vn is very positive, it looks like that. But where's the crossover? Okay. And the crossover you get when you set these things equal to each other. Okay. So we say V out is equal to Vn is equal to 0. And okay, lo and behold, basically the crossover is when V out is equal to Vn is equal to 0. So if I was gonna combine these things, and hopefully I did this right, otherwise I might get embarrassed. Okay, so we go between these curves when Vn is equal to V out, and anything below this, V out is equal to Vn, which means it'll look like this. Okay, anything after that point, V out is just equal to 0. Okay, so the slope is going to be 1. Now the slope is going to be 0. Yay, got it. Okay, it's always a pleasant surprise. Okay, everybody with me, like how the procedure there, and it's like the same procedure over and over again, but it just needs practice. And I was practicing before class. Arthur, do you have a question? You're just popping up. Okay. Any questions? No? Everybody's good with that? Okay. So let's do another one. So this guy. So, we initially, I don't know if you guys remember, but going back to, it was the last lecture, maybe before that, we talked about one of the big uses of diode is as a rectifier, and the rectifier would help us build like a voltage regulator, which takes AC stuff from the wall and helps us make it a DC voltage for charging up our stuff. Okay, so let's look at that, what that looks like. So, okay, so that is a diode. Whoops. Okay, so what does this look like? I do the same thing again. When Vn goes very negative, that means this point goes very low. This guy turns off, right? This point, the anode is much lower than the cathode. So that guy turns off. So the diode is open. So I'm going to draw it as an open. Okay, so we've like disconnected V in from V out. And so again, there's no current across this R1. So basically there's 0 voltage across this R1. So V out is just 0. Okay. Oops. Everybody with me? Or anybody not with me? Vn goes to positive voltage. Okay. So now this guy is very positive. This guy turns on. So I'll redraw it as Vn R1. Okay, so what happens here? Well, we have this R1, and I'll explain a little bit why we even have the R1 there. But we've shorted across, and so just V out is equal to Vn. There's no, the R1 is basically, you get a current through R1, but it doesn't matter because it just V out just is shorted to Vn. So some current flows, but V out is just equal to, whoops, what is going on with my pen's acting up. So V out is equal to V in here. Okay. So again, as idiotic as it is, I'm just going to be consistent. So I'm going to again look for the crossover point. And that is going to be V out is equal to 0 is equal to Vn. So I'm just basically setting this equal to this. Okay, so basically the crossover point is at V in, V out being 0. Okay, so if I was going to plot this as a V in versus V out, I would end up with below 0, which is our crossover point. I have to use this equation. So V out is just 0 no matter what V in does. And after a crossover point, I use this equation. So V out is equal to V in with a slope of 1. Everybody good so far?
Is that graph for the crossover point?
I'm sorry?
Is that graph that you wrote, is that for the crossover point? Or is it just for the, if VLN is positive infinity?
Sorry, you're getting muffled a little bit, Arthur. So you're asking if I'm just doing this
I'm
graph?
just asking for the graph itself. I'm not sure, is that for the crossover point or?
Why do we just do this graph? Is that kind of the question?
No, I'm just asking if that graph is for the crossover point.
It's for the entire range of V in versus V out. But I'm not sure if you mean, like, Arthur, do you mean why are we doing the graph, or what is the graph telling us? I mean, the graph is giving us the entire range of V out versus V in of this circuit.
I think he was just confused because of where you placed the graph. I think that's why.
Oh, I'm sorry. I'm sorry.
Yeah.
Sorry. Thank you. Thanks. No, this is for everything and everything. I'm sorry. Yeah, this
Yeah,
is,
that's what I was trying to say.
yeah.
Yeah.
It was for everything? Okay.
Wherever
Okay.
you like it. Where would you like it? Anywhere you like. Okay. So the reason there was a good reason I put it there, but maybe I should just start a new page so that it won't confuse you. I thought there was a good reason I put it there. Can I copy it? No, I got to copy it over. So I'll put it on this page. Okay. So this is our V out versus V in, and it's just like the full range of V out versus V in functions. Okay. So that's one graph that we have a few different graphs in this class, like 3 graphs in particular. Okay. And you'll see those over and over again. Okay. So one graph is V in versus V out. For this, I'm talking about, these are graphs for the same circuit. Okay. There's like 3 things we tend to represent: V in versus V out. Then you've also seen graphs of, say, the voltage across a diode and I sub D, or just more generally, voltage versus current. Okay. So for example, the exponential curve was an example of that, right? But it's just a general statement now. I'm making a general statement that you have voltage versus voltage, so V in versus V out. You have voltage versus current. Okay, so we've seen examples of those. And the third one, I kind of snuck that by you guys a little earlier. We also have, we haven't looked at this very much, but maybe a couple of times, we also have voltage versus time. Okay, again, these are all for the same circuit. Okay, so for example, the circuit, I just drew V in versus V out, but I can try to plot V out as a function of time with a given V in. So for example, here, let's assume my V in was like this. It's supposed to be a sine wave. And let's say if that was the 110 volt RMS peak. So it's a 110 volt signal. So this is 110 volt times square root of 2. This is 110 volt times square root of 2 minus. Okay, so this is like indeed the voltage that comes out of the wall in the US. Okay, and you know the peak to peak frequency is 60 hertz, or in time it's 16.6 milliseconds. Okay, so let's say that's our VN. Okay, so that's VN. So let's say that's our VN here. Okay, so then let's look at what V out would look like. Okay, well, anytime Vn, so anytime Vn is less than 0, anytime here, V out is equal to 0. So Vn is less than 0 here and here, right? So if I was going to draw V out on top of this, so green is V out, green is V out, I would just go like that here. It would just be 0, right? Because now I'm just drawing V out, and it would be 0 here. You guys with me?
Yeah.
Okay. And then anytime Vn is larger than V out, okay, V out is just equal to Vn. So it's here and here, V out is just equal to Vn. So I just draw that V out on top of Vn. So and I end up getting these. I only let the only thing that goes across. So if I redraw this circuit, so if I have this circuit, the only voltage that this circuit will pass through are positive voltages, and it'll block all negative voltages and sort of shorts them to ground. Okay, I mean, this is, you know, what you see here. So this is called rectification. Okay, and it's sort of the first step to get rid of. So this input, like we said, is purely AC, meaning it has 0 DC component. But this, because there is no negative component to this, it does have a DC component on the average. Okay, on the average, if you take the average over a full cycle, you'll have a DC component. It looks ugly and so on, so you got to do some other stuff to it. But it's the first step towards us building our wall plug. Okay, so that's the third type of graph, which is time versus voltage. And it just depends on what the problem, and you know, in this class, it depends on what the problem is asking for. In the real world, it depends on what problem you're trying to solve. Okay. Now, lastly, any questions so far? Okay, one last thing is, why do we have this resistor? It didn't show up anywhere really. I mean, it was like sort of, you know, it almost looked like we could live without it, right? It didn't show up in any of our equations. It was just sort of like this, either it was like shorting one way or another. Okay. The thing is, if in this case, where you're going negative, we're in this negative range, when this thing is open, okay? So if there was no resistor, so if R1 was going to be, didn't exist, okay? And we'd end up like this. So anywhere out here in Vn being, oops, I shouldn't have done that. Anywhere, okay. Anywhere out here when Vn is negative, if there was no R1, V out would just be floating. Unless, you know, you've got a sampler, like you put a capacitor here, as we'll see, like to keep the value, keep that charge. Like a floating node with 0 capacitance or no capacitance is like a total disaster. You never want that. Okay. In fact, if you try to do that in SPICE, Like your simulation will not allow you to do stuff like that, because this voltage floating with, if you don't have a capacitor or something that like sets this to something, it could float, and in reality will. It could float to minus 10,000 volts. It could float to minus 1,000,000 volts. It could do anything. You just don't know. So you never want a floating voltage anywhere. Bad, bad, bad. So basically what this resistor does is it makes sure that when the switch is open, this point, this V out is not floating and is anchored to a certain voltage, which is ground. Okay. Otherwise, you just end up with a floating situation, and like nobody knows what that voltage is, and not just theoretically, but in reality, that voltage could end up being anything. It could like destroy your circuit. It could stop your microprocessor from working. Periodically we get, like very rarely, thankfully, we get like a floating node accidentally in a circuit in our chip, and like it's just, you're done. So anyway, so that's what that resistor is for. Okay. All right, so then we have the signal strength indicator, which is one of the nice things, but I'm not going to go into it just because it kind of like stops our flow of our thoughts. But it's another use is if you actually, what it basically says is if you integrated the signal after a rectifier, if you somehow could build a circuit, which you can, to integrate the voltage across this, you could get an amplitude that it would indicate, so like a DC voltage that would indicate how big this signal is. Okay, so a lot of like RF circuits, like in your cell phone, some fiber optic circuits, but you guys aren't, that's sort of harder to get your arms around. But say your cell phone, if you see it's got, bars saying the strength of the signal, right? Those bars are basically looking at the input signal, doing this rectification and integration across this half cycle, and giving you, like giving the cell phone a DC, some voltage that says, I'm strong, I'm weak, I'm this, I'm this value, that value. And basically this is just, basically integrating across sine wave, that's 0 for half the cycle and some value in the other half of the cycle, and it ends up giving this output voltage that on the average is related to the peak voltage. Anyway, okay, but I won't go into that. Don't think we're gonna see that in a quiz or test. Okay, again, I didn't want to stop the flow. Okay, which is ad nauseum doing these analysis. Okay, so here's another circuit, which is, let's see what we're gonna do. Oops, I'll put that page in the wrong place. Okay, so we got this guy, right? We got a voltage with a diode and a battery. So, whoops. I get this right. V1. I guess they call him V1. Is 1 volt. His V battery is 1 volt. Okay. But by the way, something that's lost in all this stuff is, is like, if you were gonna do this with our exponential or natural log equations, it would take a lot longer, and I think we'd end up with a lot less. We'd end up with a more accurate value, but probably a less overall feel for what the circuit will do. just because, I mean, look at how it's, you know, after enough practice, it's already fairly easy, right? To end up with these curves by just doing these diodes as an on-off switch. And I think it gives you a better, like a feeling, a better indication of what the circuit's doing, okay? And, you know, there's nuances that happens when you do have the exponential, but again, I think this gives you a better top level feel. So that's what we're trying to just get enough practice with this on-off business. Okay, so let me check out my notes. Okay, cool. All right, so we do, once you guys take a crack at this, I'll give you guys 5 minutes. I guess you can always cheat and peek, but then I'm going to call in your name and you'll have to explain it. So try to give it a shot, and I'm going to call one of you guys to help me out. Oh, which one? This thing? No, I'm sorry. This guys, this is a battery. This is a battery.
Wait, so what are we supposed to be finding here? Are we supposed to be finding a value or just
So what you want to do is figure out, let's figure out V out versus V. So we want to
figure it out?
create this, but very good question. Sorry, I didn't say that. So we want to complete this curve, V out versus V in.
Got it. Okay.
And the answer is in the next page, so you guys can cheat if you want. Okay, guys, let's try to do this together. Anybody want to volunteer before I volunteer somebody? Going once, going twice. Nelson, you spoke last, so I have to pull you in first.
Oh, okay.
So how did it go?
Well, is it just if it's V in is infinity and V in is negative infinity, right?
Yeah, let's try that.
So I guess if V in was infinity, then V out would probably go up, right?
hold on a second. So we want to say if
Okay.
V in goes to positive infinity, okay.
Then V out should be positive, right? It should be going up, like
So this point is positive. Yeah, so this is like positive infinity over here.
yeah. So it should be like exponential, sort of, right? And it goes up.
Uh-huh. So remember, we're using like the simple model here of this diode being on or off. So if this point goes way up, so this point is at plus, like this diode, this battery, make sure this point is at 1 volt. Right?
Yeah.
And so you just said V1 is going to go to infinity, right? So what does that mean?
So that means this is just like but it is a short, right? So it's just one wire just connected.
Yep, that's all you do is you just redraw this as if it was connected and you had it was going. So just redraw the whole thing.
Oh, so does that make V out just 1 then?
Yep.
1 volt?
Yeah, just 1 volt. Exactly.
Okay, yeah.
So V out is 1 volt. Okay.
That makes total sense.
So,
Wait, I have
sorry? Go ahead, guys.
the V1, then that would mean that V1 had no considerable voltage if the output's 1 volt.
Right. Basically, you have like a fight between V1 and
VBAT.
Yeah. So the battery, just assume the battery is perfect and V1 is not. That's a real good question. And in reality, what would happen if you connected 2 voltage sources together like this is they would start pulling current from each other until one of them could produce more current than the other one, and that one would win.
So in this case, you just charge the battery if V1 was greater than VBAT.
Yeah, this is like a ideal battery. So don't think of it in terms of charging and discharging. Just think of it in terms of a voltage source. It's a voltage source that's like constant and will always win.
Okay.
Yeah.
It can supply infinite amounts of current.
It can survive. Yeah, it can supply infinite amount of current. Yeah. That's a very good question, though. Yeah. Does somebody else have a question? No? I thought somebody else popped in there for a second. Okay, so back to Nelson. You got a short reprieve, Nelson.
Oh, I have to do the other one too? Okay.
Yeah.
Okay.
We gotta do the whole thing, man. Come on.
Oh, okay.
Just
All
like
right.
a test.
All
So
right.
Vn is negative infinity, right? So this guy,
So it should be open, right?
yep, open.
And so that means there is no voltage, right? Because it's not connected.
That's what I thought too. Should be no voltage because the grid circuit is incomplete.
Yeah.
Be careful there, guys.
Wouldn't it still have the V in?
Yeah, because like V out is now just connected to V in.
Wait, but didn't you say you're not supposed to do that?
Sorry?
Didn't you say you're not supposed to just have like the wires? Oh no, that's if it's disconnecting the whole thing.
Yep.
Like if it's isolated the whole thing. Yeah, yeah. Okay, never mind then.
As soon as you open the switch, the battery just, V out doesn't look at the battery anymore, doesn't see the battery anymore. So the only game in town is VN, and V out is just connected straight to VN. So in this case, V out is just equal to VN. Okay. So you just need like, you just got to do this over and over and over again until like you start like, you know, it gets more complicated. So, but anyway, we're starting from scratch. Okay, last thing, Nelson, is the crossover point. Okay, and the crossover, at the crossover point, remember the meaning of the crossover point. At the crossover point, both of these equations must be true. Otherwise, the two lines wouldn't connect to each other in that crossover point. So both of them has to be true. So basically you set them equal to each other. So V out is equal to V in, and V out is 1 volt. So V out is equal to V in is equal to 1 volt. So the crossover happens when V in is equal to V out. Both of them are 1 volt. Okay. So now help me draw this V in versus V out.
Oh, now we're just putting together. Okay, so I think it would be
My advice is to start at the crossover point.
so start at, well, I guess it's gonna be, well, the voltage is gonna be the same up until like 0, and then after that it'll go to 1 volt, right?
No.
No?
Crossover.
I think it will approach 1 volt, but I don't think it's gonna reach 1 volt, right?
See, like,
Actually,
think about it this way, guys. Like this, anything could happen here. Like you could do, so in the negative region, V out is equal to Vn. So the graph is always going to look like this. Okay. And then afterwards, V out is equal to 1 volt. So it's always going to look like this. So the question is it going to look like this? Is it going to look like that? 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 You don't know, right? Although we know what happens at very negative, this happens, right?
yeah.
And we know what happens at the very positive, we know this happens, but we need to know when this and this connect up. And this, that's the crossover point. And we just calculated that, the crossover point. So the crossover point is when V in is equal to 1 volt and V out is equal to 1 volt. So that's so anything below this is V out is equal to V in. So it's a slope of 1.
Oh, so it's just a straight line.
Yeah.
Well, it's a straight line till 1, and then after that it becomes constant after that.
Yeah, it becomes 1 volt. Okay, so this is the importance of the crossover point, because it's possible, and you'll see this, that we can get other types. You know, you could have had the crossover point at 0. You could have had it like any number of places. Well, no, I'm sorry, I'm being excessive here. Like could have done any of these things. So that's why I said start at the crossover point. And the crossover point. So we got one line and then another line, and you need to know where they cross, and that's the crossover point here. So you start there, and then everything below or less than this is this equation. Again, it'll just be a straight line, V out is equal to Vn, and anything past the crossover point, this way, V out is 1 volt.
Oh, I see. So basically it's just, if you find at negative infinity and positive infinity, they're basically two equations. You just got to find where they intersect.
Exactly.
That's basically the crossover point. Okay.
Exactly, because it's like by definition, at some point they're going to transition between those two equations, and at that point both of those equations have to be true. Otherwise you'd have a like I want to draw something crazy, you'd end up with like something like this or something, like you wouldn't connect up. So it wouldn't make any sense. Okay. Any questions, Nelson?
Actually, I do have one. So, I guess yeah. So basically, if you put voltage into a diode, right? Didn't you say there was like VD or something? Right. So what happens to that? Does that just disappear or?
Well, so right now we're playing with the ideal diode model. Okay, remember this is a real diode, right? With all this equation. Okay, that's kind of our real diode. But what we said is we've cooked up an ideal diode model just to make life easy for us. Okay, just to make life easy for us, we created this brain dead model where if the voltage across the diode is positive at all, it's a short, and if the voltage across the diode is negative at all, it's an open. So this is like our first level of brain dead model, and you'll see this over and over again in circuit analysis. Is especially hand circuit analysis is a game of approximations. You kind of want to get a feel where things are. If you start doing like full set of equations for all your circuits, and like most of your circuits are not going to be one diode and one resistor. It might have like 5 diodes and 20 resistors and probably like 15 transistors or something. You're just going to get nowhere. Okay, so what you do is when you're doing circuit analysis and this is like the real life and probably the lab for Cal Poly and future classes you guys take, is you've got these really simple analysis methodologies. Like one is this one, which is on or off diode. And then there you get a rough idea what your circuit's doing and the relationships, okay, like what your circuit's doing. And then you can build a circuit in the lab, in 2200L if you guys are, if the classes are in person, you're taking that, you'll actually probably get diodes and resistors and stuff and plug them in and put a voltage in and look at the output. But if you don't know what to expect to begin with a simple hand calculation, you'll be my friend used to call it being a monkey in a cage. You're just sort of trying random stuff, hope, you don't know what's gonna happen. So you need to begin with a real rough estimate of what's going to happen, and then either you create it in the lab and that'll be a physical thing that you made, a physical circuit, or the other thing you do when you're doing chip design, or sort of maybe if you're doing a sort of virtual lab, you do use SPICE, like a simulation tool that's very accurate. But if you try to do either one of those, the lab or the simulation tool, without knowing what to expect and without knowing the relationships, you're just going to be randomly tweaking parameters, resimulating, and you're not going to get anywhere. Okay, so right now, Nelson, we're dealing with this ideal model. Okay, now we'll go back to, like, if you do the homeworks, which again, I strongly suggest, sometimes you have to use, and we'll talk a little bit about that probably in the next lecture, this exponential model. Sometimes you just have to use it. And then there's yet another model, which is somewhere in between. It's a little more complicated than the ideal diode model, but not much. And then, in the tests, and then sort of in real life, once you get experience, you'll know which of these models to use. Okay, so you'll have 3 models to pick from. Simplest one is this ideal diode model, on or off. The most complicated one is this exponential model. Unless you have to, you don't want to use that model. It's too time consuming. Okay, and there's yet another model that's like somewhere in between. Does that make sense, Nelson?
Yeah.
Okay, so everything we're doing, like in the lecture today, essentially all these problems we're solving is with this ideal diode model. And like in the homework and in the test, it's you get pretty, like I will, or the text gets pretty specific about which model to use. Okay, because like again, we're trying to make you guys get practiced in analyzing with all three models, and also you guys don't have a feeling yet probably for which model to use when. All right. Okay. Any other questions?
I've got a question, Professor.
Yeah.
So I see that we after V1 on the x-axis, it just has a flat line. Does this mean that we can't go past any output voltage of 1 volt?
Yep. Exactly.
So what would happen if we put like 3 volts at the input, and we have this just that 1 volt? It's just always going to be 1 volt.
Yep. Yep. So what's going to happen is, if, again, our assumption is when you see something like a battery has got some voltage across it, and then the current is going to be like, it could be anything. It could be infinite or whatever it is for it to be able to support that voltage. So we're saying if you put a voltage source across this, like this will have some, like a lot of current output, but not enough to beat this guy. Okay, so you could, I have done this accidentally, let's say, in the lab. So if you take 2 voltage sources and you short the outputs together and try to crank them up and down. I don't know if, do you guys have you guys used voltage sources and stuff? Been in the lab?
Really?
Not? Well, okay. So, I mean, these are like these in the lab, they'll look like these big boxy devices, and there's a voltage, and you can actually change the output current of these voltage sources. But if you short 2 of them together, they have, each voltage source has its own rating of how much current it can supply. So, some of them are like 1 amp, some of them are 20 amps. But if you hooked up a voltage source that was a 1 amp output, you shorted that to a voltage source that was 20 amp output, then no matter what the voltage source with the 1 amp would do, you would always get the voltage coming out of the 20 amp voltage source, because it would just eat that current and collapse the other voltage source to its own value. It would always win.
So when you say short, you mean like connect both anodes together?
Yeah, or just the voltage source has like 2 outputs. It has a ground and voltage. So if you hook up the 2 voltages together and the grounds together, and you try to make one 20 volts and one 1 volt, the output voltage that I can supply the most current will win. So if the 1 volt supply has 20 amps output, and the 20 volt output has 1 amp output, they'll just peg to 1 volt, or vice versa.
Got it. Thanks.
Sure. Yeah. Yeah, it's too bad you guys don't have experience with voltage sources and stuff, but you could try this also again. And I don't know if you have experience with Spice. You could try it with like Spice to see what happens if you short voltage sources together. You'll just get a huge amount of current going between the voltages. And the one that can source the most current will win. Okay, guys. Well, that we're out of time today. So I'll put in a homework, all the homework problems for 3, so you guys can start playing around with this. But you'll just see a lot of this, just like circuit practice with this model. Again, we'll bring up another model, and then also the exponential model. Any questions? Any more questions, anyone? Okay, guys. So have a great weekend. I'll see you guys on Tuesday. Take care.
Thank you.
Thank you,
Have a
Professor.
good day.
Thank you, Professor.